Swayam Prabha. Digital India. Educated India.
So you can solve this kind of equation to figure out how electric fields change as a function of position and time. Now that we've addressed the question of setting up a coordinate system and of dynamics given a particular coordinate system, we come to another interesting question, which is, how do different observers correlate their observations of dynamics? So how do different observers compare their observations? Because after all, every observer is free to choose for their spatial coordinates. Every observer is free to choose an origin, a set of reference axes, and their unit length or standard length, okay, or meter stick. And for their time coordinates, every observer is free again to choose an origin and a reference time interval. Okay. Now, intuitively, we expect that differences in these choices, the choice of origin, the choice of set of axes, the choice of unit length, or the choice of origin, reference time interval, these choices should not matter in our description of the physical world. Okay? And indeed, this is true for a set of observers whom we think of as inertial observers, that is, observers who are in a state of uniform motion relative to each other. Okay, so first let's take a simple class of observers. Let's take two observers who are at rest with respect to each other. But let's just imagine that the only difference between these observers is that they choose an identical time origin, that is, they have the same clocks and they start them at the same times. They have the same reference time interval. They have the same set of spatial axes. They have the same unit length. But let's take two observers who differ in the choice of origin of their spatial axis. And let's ask if for these two observers, how do they describe the world and how do they relate their different observations to each other? So let's take one observer here with origin O and coordinates x and y. I'll just take 2 dimensions for simplicity. And let's take another observer who chooses to set their coordinate system in such a way that they are displaced from this origin by an amount a. Okay, so their origin is over here and their x-axis is, let's say, has the same orientation. And their y-axis has the same orientation. And they also have the same meter sticks. So this is 1 meter, and this observer also has same 1 meter stick. Okay, and now they want to describe the position of a particular particle. So they want to describe position of this particle, let's say over here. So what would observer 1 do? Observer 1 would say that with respect to my origin, this is the vector that describes the coordinate of this particle. So let me also define these observers. So let's call this observer 1. And let me define this as observer 2. And observer 2 would draw a different vector and say this is the vector that I'm going to use to describe the position of this particle. Now both observers are describing the same particle, okay? And the other thing is they're also they have clocks which they've agreed on the origin of time and they've agreed on their interval of time. So we would also say that both observers are measuring this position of the particle at the same instant of time. Okay, so in observer 1's language, this red T describes their time that they measure. Oops. And for observers 2's language, this blue T describes the time that they measure, and these are the same. So for clarity, I'll denote observer 2's observations with a prime. So I will put a prime on this, okay? And the time interval measured by the time coordinate of this particle's position is T prime. The time coordinate of this particle's position according to observer 1 is T, and those two times are the same. The numerical values are the same. However, they disagree on the position of the particle, or at least their description of the position of the particle. They both agree that the particle is there. They just have different ways to describe what there means. So according to observer 1, the particle has a coordinate, which I will describe by the vector x bar, which is this pink line over here. And according to observer 2, the coordinates are described by an observation x prime bar. So to relate their observations, we need a dictionary. Okay, the dictionary tells us how to relate this quantity x to the quantity x prime. Okay, x and x prime, but also t and t prime. In this case, the relationship between t and t prime was simple, but that is still part of the dictionary. Okay, so how do we make this correspondence between x and x prime? Well, it's easy to see. Okay, so if we go to observer 1's coordinate system, then they would say that there is a vector which I will denote as the vector A vector, which has magnitude A, which describes the displacement of observer 2's origin with respect to my origin. That's what observer 1 would say. And therefore, by simple laws of vector addition, they would say that therefore the vector x bar would just be the vector sum going from here to here. So in other words, it would be the same as a bar, which is let me go this way and then let me go this way. So it would be this amount. Okay. So this is the dictionary. Okay, it's a very simple dictionary. It basically says that the vector x as described by observer 1 is related to the vector x prime as described by observer 2 by a simple shift of the vector by a constant vector a bar. So a bar doesn't change with time. The important point is a bar does not change with time because we're assuming that observer 2 is at rest with respect to observer 1. So for any instant of time, now we can write down this relationship and we can say that the dictionary at any instant of time, so this dictionary is always valid, is given by t prime is t, and, or let me write it the other way. T is the same as t prime. Both observers measure the same time. And the observer x measures a position which is related to the position measured by the observer 2 by a constant shift. Okay, so here a bar is independent of time. Which means that since this dictionary is valid for all times, it should be true that if the position of the particle changes, so it's now at a position x bar at some time t in the future, in the old observer's coordinate system, it would be at x bar at time t. In the new observer's coordinate system, it would be at x bar prime at time t prime. T and t prime are the same, okay, with our dictionary. And the relationship between them is still the same. X bar of t is x bar prime of t prime plus this constant shift, okay, by a bar. That's easy to see, right? You imagine that this point has moved somewhere else at a future instant of time. Again, it's the same relationship. If it moves to a different position, let's say over here, this would be the new vector x bar at some other instant of time. This would be the new vector x bar prime at that new instant of time. But again, their relationship would be the same. X bar, which is this displacement, would be this displacement would be the same as the displacement along this x-axis plus this displacement. So again, x bar would be a bar plus x bar prime. So this dictionary is valid at any instant of time, and it allows you to translate, okay, allows translation between different observers, okay. So the dictionary is specific to these two observers, and these observers, what defines the relationship between them is the amount of displacement a bar, okay. If I have a third observer with a different displacement, let's say b bar, then I would have to put that different vector over here, okay. So this dictionary relates two different observers. So you think of this dictionary as a language dictionary, okay? So it's a language dictionary. For example, if I'm translating from English to Hindi, we're saying the same thing, okay? In English you say cow, in Hindi you say guy, okay? These mean the same thing, but you still have to make the translation. You have to make the correspondence between English and Hindi. Once you establish this correspondence, you can now start talking to each other, okay? You can see that you're really describing the same thing, you just have different words for it, okay? That's exactly what's going on over here. You have different words to describe the same particle, the position of the same particle. You have different time coordinates, you have different position coordinates, okay? Different observers are using different time coordinates and different position coordinates. If I have a third observer, for example, let's say someone talking in French, okay, the word for cow is vache, and so they have a third word for it, okay. So this would be like relating these two by a vector A, these two are related by a different vector B, okay, but there is a way of going from one observer to a second observer to a third observer and so on. So this kind of change of observers by motion, by moving along a particular direction in space, is called a spatial translation. Okay, it's a translation just as an English to Hindi translation. Different observers are just talking about the world in a different language, but they're describing exactly the same physical things. All right, now that we know how to establish a dictionary between two observers who are at rest with respect to each other, let's ask a different question. Let's take two observers, but let's suppose that the first observer is here, and they have coordinate system x, y, and clocks of time interval t. Let's assume a second observer who again has exactly the same setup that we had before. So they have the same choice of axes, they have the same length scale, they have the same meter stick, they have the same choice of origin in time, and they have the same choice of time interval. But they don't necessarily, and let's suppose that they even have the same choice of origin in time. Let's suppose they have the same choice of origin in time and space. So when time is 0 for the first observer and time is 0 for the second observer, and their dictionary is t is equal to t prime, both their times agree. So they have the same origin at their 0 instant of time, but let's suppose observer 2 is not static. Okay, let's suppose observer 2 is now moving with respect to observer 1, and the way they're moving is that after some instant of time t, they are displaced by an amount a. Okay, but this a is not independent of time, it's a function of time. So the displacement of this origin, let me call this origin O prime, and this origin is O. Okay, the displacement of this origin is a function of time. Okay, as a function of time as measured either by the first observer or the second observer, it doesn't really matter since both their times are the same. And now we ask, what is the dictionary that relates observations between these two different observers? So observers in a state of uniform relative motion. So by uniform relative motion, what we mean is we won't just assume that a bar is any arbitrary function of time, which means that the second set of coordinates is not moving in an arbitrary jerky way as it moves forward, but rather it is something like this. It's a constant vector. Let's call it v naught, or let's call it v relative. Okay, so that times time. In this case, I've taken v relative to be along the x-axis. Okay, so this displacement, which is a bar, is no longer a constant. It's changing with time. So as time passes, this origin will move further and further to the right. Okay, and now we want to know how to make translations between these two different observers. That is the observer O and the observer O prime. keeping in mind the fact that this observer will be displaced at future instants of time with respect to observer O. So that's very simple. We would just say, using our old dictionary, T prime is T, and we would say X prime we would say T is the same as T prime, and X vector at time t, so the position of a particle at time t, would be the same as the position of a particle described by the second observer at time t prime. Those instants of time are the same, but there would be a shift by a vector a bar, but this is now a function of time. Okay, and in particular we're taking the specific case where this is a constant vector times a time interval. So this is more general for arbitrary motion of these observers relative to each other, and this is specific to observers in uniform relative motion. Okay, so this is for arbitrary, possibly jerky motion. Okay, so this is a specific case of this dictionary when the observers are in uniform relative motion. Now let's ask what happens to the laws of dynamics when I translate between these two different observers. So this is the next key question that we will ask. What happens to the laws of dynamics when I translate between these different observers? Okay, so let's take Newton's laws. So F is equal to ma. And let's suppose both observers see the same forces acting on the particular particle. So let's suppose there's a contact force which is pushing the particle, and both observers agree that this is the same force acting on this particle. Okay. Now, this acceleration is d square x by dt square, but this coordinate x is different for different observers. So observer 1 sees x bar as a function of time, and the velocity or the rate of change of this coordinate, this particle is at location x bar, and now it moves to a different coordinate x bar plus dx bar in a time interval dt. So you would say that the rate of change of its position, that is how much it moves in a time t, this is its velocity at time t. And if I want to know its acceleration, I would calculate the rate of change of its velocity. That is, I would calculate the second derivative. And so we want to make a translation between what observer 1 sees and what observer 2 sees. Observer 2 would see a position x prime which is related to x by this relationship. Okay, I just simply took the a bar to the other side of this equation. I just moved this quantity to the other side of this equation. And therefore, the speed that they measure, now here's something important. The speed that they measure is the change in the position x prime divided by the time interval that has passed for observer 2, and their time interval is t prime. But since we know that the dictionary also tells us that t prime is the same as t, so the speed as measured, or the velocity as measured by the second observer, is the same as this, and x prime is also can be written as this. Okay, and so now if I differentiate this further, what I get is dx bar dt minus so this is a dictionary that we've now derived for velocities. Okay, so observer 2 would see a velocity v prime which is related to the velocity v seen by observer 1 minus a vector that tells us the rate of change of this vector a bar, which is the displacement of this origin, as a function of time, the rate of change of that displacement, okay, with time. So let's take the specific case. Okay, so this is general. Let's go to the specific case of uniform motion. So if the second observer is moving with a bar of t being this constant vector vr times t, so it's moving with a constant speed or constant velocity with respect to the original observer, observer 1. In that case, v bar prime would be v bar and this would be okay. So this is now specific to uniform motion.